All right, last video, number 14, nuclear chemistry. Nuclear chemistry is a short one. A couple of definitions, but a lot, couple practices, a couple of things that you kind of just need to know. And let's cover the main topics of nuclear chemistry for the New York State curriculum that you will need to know for your Regents exam. Let's cover it. Nuclear chemistry has to do with radioactive elements. And radioactive elements are titled that because their nucleus is unstable. And what classifies an unstable nucleus is the emission of some particle from the nucleus. So sometimes that's alpha, sometimes that's beta, sometimes that's gamma. But something is coming out of the nucleus. That's what radioactivity is. The first type of radioactivity that we talk about is natural stuff. And we call this natural stuff natural transmutation. And transmutation is when an element turns into something else. Specifically, natural transmutation is when it happens on its own. And so one reactant is going to become a different element. The most important thing about identifying a natural transmutation is the idea that we're starting with one reactant. So carbon-14 is something that is a natural transmutation. It will spontaneously decay on its own after a certain amount of time and become something new, right? So nuclear stability depends on the proton and neutron ratio. Anything that's over atomic number 83 will be naturally unstable. It's just too big. So if there's natural transmutation, there will also be artificial transmutation. Artificial transmutation. And this is different than natural because it's two reactants become a different element. And basically, some nucleus has to be hit with a different particle, whether that's a neutron or a proton. The nucleus of a stable or unstable nuclei gets smacked by something else and turns into a different element. And that process can happen one or two ways. We can have a fission reaction and we can have a fusion reaction. These are two different forms of artificial transmutation. So when particles smash into one another, they can undergo fusion or they can undergo fission. And those, that's an enye. Fission or fusion. I think I threw an I in there and it doesn't belong. I'm not a English teacher. But fusion is when the two particles that collide. Fusion is when the two particles collide and make something bigger. So if hydrogen and hydrogen smash into each other, and in the result they combine to make a helium, that would be called fusion. It's a bigger atom. It's got more protons. It's got more neutrons. Fission is the opposite, where two particles smash into one another and out comes smaller nuclei. Uranium-235 tends to do this. It gets hit by a neutron and splits into two smaller nuclei. Even if it diminishes by only one proton, it's considered fission. right? Because it is breaking to something smaller. Now, the other comparison between the two, fission and fusion, is that fusion, the process of making a bigger element, produces more energy than fission. So the process of making larger nuclei makes more energy. The sun is the biggest ball of fusion that we have. Constantly, hydrogens are smashing and making heliums. Heliums and hydrogens are smashing and making lithiums. This whole process is what gives the sun as all the energy that it outputs. All that heat and radiation coming out of the sun is a product of a fusion reaction. Now we can get a little bit more specific with radioisotopes and what they do. Certain ones, but typically radioactive isotopes that have short half-lives, I'm going to abbreviate half-life into HL, okay? Half-life. They're commonly used in the medical field. And that makes a lot of sense because you don't want radioactive material in your body for very long. So half-life is the amount of time it takes to decay a radioactive isotope. So if something has a shorter half-life, its radiation will not be in you for as long as something with long half-lives. Now, long half-lives, like carbon-14, is used to date the age of living organisms. Uranium is also used to date non-living things. They have half-lives of thousands of years, if not millions of years. And we don't want to put those sorts of things in our bodies because they would be there for a very long time emitting radiation. A couple of things to finish up. Nuclear reactions do not follow the law of conservation of mass. They do not follow the law of conservation of energy because they're taking a small amount of mass that exists and they're turning the mass into energy. This is where that energy is coming from. You can't make energy. You can't destroy energy. You can convert types of energy. And in these types of reactions, the energy conversion is coming from the mass of the particles. So whether it's a fusion reactor like the sun or a fusion reactor that's on Earth, a fission reaction like a nuclear bomb or a nuclear power plant, whatever it is, it's taking the mass of those radioactive isotopes and it's turning it into the energy, which we then use to convert into electrical energy for houses and up to go. So fusion has more than fission. Lastly, the penetrating power of radiation. Alpha, beta, gamma. How do they compare? Well, as far as masses is concerned, alpha has the most mass. It's got a mass of 4. How do I know that? Well, on table O of your reference table, it tells you that an alpha particle can be represented by He42, a helium atom. An alpha particle is just a helium atom. It has the most mass. It has the least penetrating power. It doesn't go through paper. It can't penetrate through paper. It's not going to penetrate through your body. Beta particles have the middle amount. They don't exactly have 0, right? Because it's an electron. But it's basically 0. Right? At the Regents level, we say electrons and positrons have no mass. But they have a very, very small amount of mass But since it's so small, it's insignificant, and for the sake of this level of chemistry, we just call it 0. But they do have mass, which is why they don't have the least amount of mass. That belongs to gamma. Gamma has the least. It is 0. There is no mass to a gamma radiation. Gamma radiation is just energy. As far as penetrating power is concerned, beta particles are in the middle. Right? They have a little bit of penetrating power. They can go through paper, right? But they can't go through walls. Gamma radiation is the most penetrating power. It can go through paper. It can go through walls. It can go through bodies. Right? It can't go through walls of concrete or lead, right? But through your regular wall in your house, gamma radiation would make it through. And that, ladies and gentlemen, is the conclusion of this series for chemistry, New York State Regents curriculum. Again, we didn't cover everything. We covered the main topics. All of this should give you a big, advantage on your test. You still have to do a bunch of practice, and you still have to, go look at the finite details if you're trying to do really well. But this should help you quite significantly. So I want to thank you for watching. I've tried to condense the whole thing, and it pretty much comes out to be, maybe about 4 hours for the entire year, which sounds like a lot, but when you talk about 160 days condensed into 4 hours, I think that's pretty efficient. So I want to thank you, and if you've enjoyed this, please like, subscribe. I'm going to try and maybe make some more videos about how to take the test, or when you're taking a test, or going through practice problems. So hopefully I can help you out a little bit more. But if not, good luck, and I wish you the best. And thanks for tuning in. Bye now.